Canning. It's the most important advance in the preservation of food in history. There are aluminum cans for your beer, tin-plated cans for your beans. If you drink it or eat it, it probably comes in a can. Pop, chop, or peel. The technology of opening cans has changed over the years in surprising ways. Some cans keep your food safe, while others keep you safe. And although the essential can design hasn't changed much over the decades, it's still evolving, even going so far as to cook or cool your food for you.
Two of the newest technologies we're developing are ways to produce containers that can heat and cool beverages automatically. In the first case, a self-heating can uses chemistry to heat the contents. There are two reagents inside this container. There's a little bit of lime and a little bit of water. To activate it, the consumer presses a button on the base that breaks the seal, mixing the water and the lime, which starts the reaction. As those two reagents mix, the consumer will slowly turn the can, just allowing some mixing to occur. And in 3 minutes, the beverage is about 70 to 80 degrees hotter, so about 150 degrees, which would be a good drinking temperature for a cup of coffee. This is a self-chilling container, and it uses a completely different approach.
The can uses heat and evaporation to cool a beverage. A user twists the bottom of the container, which releases a desiccant, which is a water-absorbing substance. The outer shell of the can is filled with water, and when the desiccant mixes with it, the water evaporates, which requires heat. That heat comes from the enclosed beverage. The heat is then absorbed by vinegar salt located in a heat sink chamber in the bottom of the can.
So if this were a room temperature beverage of 70 to 75 degrees, it would cool it to about 40 degrees Fahrenheit, the temperature of a typical refrigerator, in about 3 or 4 minutes.
Self-cooling cans. A clever invention indeed. Yet no matter how much you jazz up a can, it's one of those inventions that seems to get no respect, even if its impact has been monumental.
We take the can for granted today. Yet when you think about it, it's probably one of the great inventions of the world, like the wheel or the light bulb. It's a ubiquitous part of our society. Everybody has them, but without it, you couldn't have moved food from the fields, preserved them, and given people the opportunity to travel and take their food supply with them.
The process of manufacturing a food can begins with sheets of tin plate, which is steel covered with tin. The metal is also covered with a coat of protective enamel.
We put enamel on the outside of the can for protection on corrosion, so it'll have shelf life, along with enameling the inside of the can that will protect the food from the container and the container from the food.
The strength of the enamel required varies, depending on the level of acidity in the food to be canned. A can of green beans doesn't need much enamel, because green beans are low in acid. But a can of tomato sauce needs thick enamel, because tomatoes are so acidic they could eat through unprotected metal within a few months. The enameled sheets of metal are first fed into a slitting machine.
The slitter cuts those sheets into blanks for the roll forming of the body. Those bodies are stacked up, put into a machine, rolled into cylinders, and then welded down the side to weld the steel together. Once we've welded the can, it goes through a side stripe system that puts a powder enamel over the area that we've welded the can. That protects the weld from the product and the product from the weld.
Next, the cans are conveyed to a dual-purpose machine called a beater flanger.
At that point, we put a flange on it, which is commonly referred to in layman's terms as a lip. That allows us to put the double seam on, which is how the end is attached to the can.
The same machine also puts beads on the can. The accordion-like beads allow the can to stretch and expand under high temperatures.
That gives the can strength from a standpoint of vacuum. The beads on the end of the can give it strength from the process cooking, which builds pressure. Once you've sealed this can and put product in it and put it in the cooker, it swells and the ends actually push outward. If those beads weren't on the ends, you would buckle the end, which would break down the integrity of the double seam.
Next, an end is attached to the can at the seamer. The other end will be attached when the can is filled with a product.
From the seamer, we test the integrity of the can through an air tester. We seal the can at both ends and put a small amount of air in it and look to see if it leaks. If we would find that the end of the can, the double seam, the weld, or the steel itself has any imperfections in it, the can would be discarded.
Once the can is tested, it's sent to be palletized. This factory produces 3 million cans a day, approximately 1 billion cans a year. During the produce season, the cans are delivered to a canning company. In this case, the Del Monte plant in Crystal City, Texas, where they're canning string beans. For centuries, the basic principle of canning has remained the same. Food is sealed in airtight containers and then cooked at temperatures usually between 240 and 250 degrees Fahrenheit in order to destroy any contaminating microorganisms it might contain.
When we bring beans in from the field, we'll go through numerous steps in our preparation process. First, we'll air clean them to get out any loose particulate matter. We'll go to a washing method to remove any grit, any small pieces that we don't want on the beans. Then we go and we snip the beans. We run them through a series of rotating drums that snip off the ends, so you don't have to do that at home.
Then the beans are brought inside the plant, where they're run through a computerized vision sorting system.
It's a color camera system. The cameras take online pictures of the product passing through this machine. The computer analyzes the picture, determines if that is a bean or not, and it rejects the items that it doesn't deem suitable. And it rejects them with a blast of air.
Next, the beans are separated by size. The larger beans are canned in the French style, and the smaller ones as cut beans. Then they're blanched at approximately 170 degrees Fahrenheit. This process locks the color of the beans and also drives out any air that might still be trapped inside them. It's all important to lose this air in order to maintain a vacuum when the can is sealed. Then the beans are put into the cans.
And they're shook and the beans are deposited down into the can, so we make sure we have a proper fill into the can. From the filler, we next go to what we call our briner or add water system. And the briner is a hot water with a slight solution of salt. And what we have there is the water drives out any of the other air in the can itself. The salt, that's added for taste.
Next, the cans move to the topper.
The topper is a rotating disc cup. And basically it comes in and it pushes out any excess water to make sure that we have a proper fill. We want to have the proper headspace as we're operating.
Headspace is extremely important in the canning process. It's the amount of distance between the top of the product and the bottom of the lid. Too little headspace causes cans to bulge during heating. Too much headspace results in underweight cans. The seamer is the machine that attaches the lids. Right before this is done, a nozzle blows a shot of steam into the headspace area, displacing any air. This is a crucial moment in the process, because part of the magic of canning lies in its ability to protect food from the decay that occurs in the presence of air. Now with a lid attached, the can has become an airtight vacuum. Next, a shelf life code is applied, indicating what day the product was canned and by what date it should be consumed. Although some canned foods can last much longer than the recommended consumption date. The cans are then taken to a giant cooking vessel, known as a retort.
What we do is we load the retort up with our crates. We can maximize 7 crates in a retort. Each batch After the door is shut, has to have the air expelled from the vessel to ensure we have a proper steam environment for cooking. The control system gives us a proper temperature and time of cook, which is all governed by the computer program.
The food is cooked inside the cans rather than prior to being canned, because this method creates the most sterile environment. No new bacteria can form in the food once the can has been sealed. The ingredients will now stay fresh until the can is opened. They're labeled, packaged, and sent off. This high-tech canning process is a far cry from the first experiments with food preservation. Ancient civilizations suspected that air was the enemy of food and wine. Over 3,000 years ago, the Greeks sealed their wine in airtight vessels using pine resin. By the end of the 17th century, winemakers began to stop their bottles with corks. Food was protected in different ways, by pouring hot oil over it or by coating it with melted fat. Many foods were preserved with salt, but that approach drained important nutrients and taste. None of these several methods could truly protect food from the deleterious effects of air. The world was looking for a clean, long-lasting preservation method that wouldn't rob food of critical nutrients. Surprisingly, the man who kicked off the can revolution was Napoleon Bonaparte, who was famous for saying, "An army travels on its stomach." Napoleon was tired of supplying his troops with food foraged in the field. In 1795, he urged the French government to offer a 12,000 franc prize to any inventor who could devise a method of preserving fresh food and transporting it to his army. In 1809, a Parisian named Nicolas Appert came up with the idea for canning. A former vintner, Appert assumed that just like wine, food spoiled when exposed to air. After years of experimenting, he found that boiling foods, such as poultry and fruits, in airtight bottles could keep the food fresh. Napoleon was sold on the idea and handed Appert the prize money himself. Soon after, in 1810, Englishman Peter Durand adapted Appert's idea. He replaced the breakable bottles with tin plate cans, which were iron cans coated with tin. The tin served to protect the iron because it rusts and corrodes much more slowly than iron. The cans were airtight. Now with cans, fresh food could be available everywhere, at any time. The new invention changed the way the world ate.
By putting it in a can, sealing it, heating it properly, you could move nutritious, high-quality food anywhere in the world. The British Navy was using over 40,000 pounds of canned food a year by 1813 because it helped eliminate scurvy and other shipboard diseases that were basically because of lack of vitamins and nutrients in the food supply for the sailors at sea for long periods of time.
Canned goods quickly spread across the Atlantic to America, where they helped feed pioneers as they trekked across the continent to settle the West. Gold Rush miners survived on canned beans, and during the Civil War, canned food was deemed almost as important for keeping soldiers alive as their weapons. Yet making the cans themselves was labor-intensive in the middle of the 19th century. Each can was handmade, with a workman hammering and soldering it into shape. A skilled laborer could usually only make from 6 to 10 cans a day. But this was all about to change with the advent of mass production. Soon millions of cans would be produced per year. During the 20th century, amazing new designs would be developed that would take canning convenience to another level. Yet one kind of can would actually threaten the very atmosphere of our planet. Americans each use an average of over 140 food cans a year. But whether it's tuna, vegetables, or jams, the canning process is essentially the same. Food is sealed in airtight containers and then cooked. Yet all of these canned foods have a problem when it comes to microwave ovens. The can itself.
There's a common misperception that metal can't be used in the microwave. That's actually untrue if you design the container properly. So, for example, this is a traditional metal can, and in fact, it won't work in the microwave. If I were to put it in and turn it on, all of the microwave energy would be reflected off of the can. So none of the energy would get into the contents of the food. If you design the container properly, such as this, so that you have a shallow metal container with a wide opening, because of that, the energy will be absorbed through the opening, then it'll work perfectly in the microwave. So the consumer lifts the tab and removes the peelable end and places it in the microwave and turns it on. So as you can see, the product is bubbling. It's been heated like it were in an ordinary container.
Microwave cans are just the latest in a long line of innovations developed by food can manufacturers. One of the biggest leaps in progress came in the late 19th century with the introduction of mass production to business. Assembly lines and mechanical body makers allowed manufacturers to produce thousands of cans per day. And these new cans were also safer.
And in early cans where they were soldered together, the tendency for leakage was much higher. The solder wouldn't withstand transport very easily. The cans would break apart. The metal would corrode. As we improved that process and the consistency of the metal, a lot of that declined. People were able to accept the can as a standard of quality and a standard of delivery that was going to be safe from things like botulism, which will kill you. Botulism is a bacteria that grows in oxygen in a can. Your mother may have told you, don't buy dented cans at the supermarket, because of the concern that if the can was dented, it might have some oxygen leaking into it, and therefore the contents of the can would be spoiled.
During the World Wars, cans and canning were responsible for keeping millions of soldiers fed.
During World War II, the Army was looking for a way to feed a soldier on the move very rapidly. And they created packaged food in cans called C rations and K rations. Everything was in cans. When you got a C ration, you got a little box with a couple of cans in it. One can would be soup or stew. Inside another one would be crackers, biscuits, and cheese.
The food can really caught on after World War II, when people began craving it for its efficiency. Now, from tuna to carrots to fruit cocktail, it was all about the can. But it's not all about the food. You'll need canned cold ones to wash down your canned meal. The use of cans for beverages now greatly surpasses the use of cans for food. The first successful beverage cans were introduced in 1935 by the Kruger Brewing Company. The containers were developed only after steel cans became strong enough to accommodate the internal pressure created when the beer was pasteurized, and when effective coatings were introduced that eliminated any metallic taste from the can. The first aluminum beverage can was manufactured in 1963. Aluminum is easily molded, lightweight, and resistant to corrosion. By 1985, aluminum cans were the most popular beverage containers in any market. Today, consumers buy soft drinks in aluminum cans 4 times as often as in plastic bottles. Recently, the aluminum can morphed into a user-pleasing hybrid.
This is one of the latest in packaging innovations. It's called a bottle can. It's made of aluminum, but it's actually shaped like a bottle. The consumers really love this because of the great graphics, its sleek look, its chillability, and its chill feel, and doesn't break like glass. It's been very popular with those in the beer and soft drink industry.
Another can that's already gotten its makeover is the aerosol can. Patented in 1926 by Erik Rothheim, a Norwegian chemical engineer, aerosol came into its own during World War II, when the American military was looking for an effective way to deal with insects during jungle warfare.
Before the invention of the aerosol can and the use to spray insecticides, the primary tool was a pump spray. It had a container that had the insecticide in it and a big air valve on top that one would pump through. Very, very impractical for a soldier trying to crawl through the jungle to pick up his pump spray and go.
The aerosol can was just the ticket. Small, lightweight, and convenient. A soldier could spray insecticides with the push of a button. Aerosol cans worked with the use of a propellant. The propellant is a pressurized gas. The nozzle at the top of the can opens when depressed. Then the force of the gas pushing down on the product moves it through the dip tube, up to the nozzle. The narrow nozzle atomizes the liquid and forms a fine mist. Early aerosol cans used chlorofluorocarbons, or CFCs, as propellants. Scientists discovered that once these chemicals were sprayed out of the cans, they drifted upwards into the atmosphere. At high altitudes, the chlorine in the CFC molecules began to break down the ozone layer that surrounds the Earth. Ozone is a gas, a form of oxygen. It serves to protect the Earth from the sun's powerful rays. Without it, we can count on more skin cancer and global warming. The CFC propellants were removed from more than 90% of all aerosols in the U.S. by 1978 and replaced by other propellants, such as isobutane and dimethyl ether. That's helped rebuild the ozone layer. However, some scientists believe the ozone layer won't return to pre-1980 levels until around 2070. Current aerosol cans may no longer be a major threat to the atmosphere, but be careful of how you dispose of them. If they're thrown into a fire, they can explode. Microwavable and aerosol cans represent technological leaps into our brave new world. But for generations, it's been a lower-tech can that's been found in practically every household where someone has a garden. Home canning has been a household tradition for nearly 200 years. There are two types of processes used for home canning.
We have the boiling water canning process, which is used with only high-acid foods. Jams, jellies, any type of soft spread like a conserved marmalade. Also includes tomatoes. And the steam pressure canner process, which is used with only low-acid foods. Things like vegetables, so your carrots, green beans, anything of that category.
A steam pressure canner is necessary because it's capable of reaching the higher temperatures needed to kill off the microorganisms found in low-acid foods. The result? Tasty food that'll last for years. From home canning fare to factory canned products, all forms of cans breed a necessary counterpart. Can openers. From the primitive to the powerful, the simple to the complex. There's one for every task. Even special openers that keep hardcore prisoners from opening up each other. It took humans hundreds of years to devise ways to put things into cans. And we're still working on ways to get them out again. Meet the titan of all can openers, Edlin Company's Model 825A.
It's the most advanced can opening system in the world. It can be operated by one user through its computer-controlled touchscreen interface. The main market for the 825A can opening system is large food processing companies, companies that are opening hundreds and hundreds of cans a day to make pasta sauces or pizzas. It can open up to 30 cans a minute or 1,800 cans an hour with just one operator.
Some companies use it to open as many as 14,000 cans per day. The Colossus is monitored by computer at all times.
The operator loads the cans into the machine through the in-feed conveyor. The in-feed conveyor is a belt-driven conveyor
with a rinse jet, which rinses the outside of the can and blows the water off the indentation at the top of the can. From the infeed conveyor, the can then enters the crown punch opener. The crown punch opener punches the top out of the can in one motion, and an alligator jaw comes in and removes the lid and deposits it behind the machine in a receptacle.
The entire machine is equipped with sensors that time every move down to a millisecond, including the dumping.
The can is then pushed through a dumping cage, which takes the can and inverts it upside down, pouring the product into the collection troughs and into a pumping station. The can continues through the dumping frame, inverting completely, and is then pushed down through a rinse jet. The rinse jet rinses out the inside of the can clean, and the can is then pushed into a can crusher.
All of this time-saving technology comes at a hefty price.
Depending upon the options the customer wants, a simple, straightforward right-line machine would cost about $65,000. Anywhere up with the options added, depending upon the processor's needs, to $90,000 or $100,000.
Over the years, much research and technology has gone into making cans airtight and strong. But there was a problem from the start: how to open the darn things. During the 19th century, little thought had been given to can openers. Soldiers during the Civil War often had to use their bayonets to pry open canned food. The first patented can opener was invented by Ezra Warner of Waterbury, Connecticut in 1858. The modern can opener with a cutting wheel that rolls around the rim was invented by American William Lyman in 1870. During World War II, soldiers went into battle with a can opener as part of their standard gear. It was called the P-38 because it required exactly 38 punctures to open the can. Consumers opened most beverages with so-called church keys, at least until 1966. That was the year pull tops were introduced.
Pull tabs worked very well, but there was a lot of controversy around them because there was a lot of litter, and there was always concern that someone was going to get cut on the edge or something like that. And the new easy open tab can, which pushes the top back into the can, was invented.
Easy open tabs are great for beverages, but today pop open tops rule the world of food cans. Now they're being rivaled by a new generation, the peel open top.
One of the latest technologies that has been developed is this new peel seam technology. So this is a flexible lid. It's still a metal barrier, so you still have the oxygen and light protection that you've come to expect from metal cans. But now we're able to open it with perhaps half the opening force of a traditional end.
Despite all of these innovations, there's still plenty of need for can openers. One of the most unusual openers has been designed for use in prisons, where convicts often work in the kitchens and might steal a can lid to use as a weapon.
Using one prison as an example, it's a high population, 20,000 or so transient prisoners, with 4 different food service facilities, and they're opening cans 3 times a day. If one lid goes missing, they have to do a lockdown of the prison and call in a SWAT team just to be able to find that potential weapon that can be very dangerous in that type of population.
This is our Model 625 APP can opening system. It was designed for a large prison in New York City. The idea is that it delids the can, takes the lid away, and securely stores it in a receptacle so that the prisoners don't have access to the lid to use as a weapon. The unit comes equipped with a can counter and a lid counter. The can counter counts up the number of cans opened, and the lid counter counts down. These 2 counters have to match or the machine shuts down and won't operate. That alerts the security officer that there's a problem. To set up the machine, you need to insert the security key and turn it to the operating position. To operate the machine, you insert a can into the unit and depress the 2 green buttons. The green light indicates to the operator when the machine has completed a full cycle.
With the machine's protective shell removed, we can see its inner workings.
The lids are stored in a secure area. The security officer has a key which unlocks the padlock and gives him access to the lid receptacle.
Used lids and cans are more than a security risk. They've also created massive amounts of landfill waste. Yet that set the stage for an effort that resulted in the savings of billions of dollars a year in electricity. The phenomenal success of the can came at a huge price. Millions of pounds of wasted metal dumped into landfills. In the 1970s, a recycling revolution took place that led to the can becoming the most recycled of all food containers.
Can recycling is the most successful environmental story. Aluminum cans and steel cans are recycled at a 50% rate or higher.
In the United States and elsewhere, billions of aluminum cans are collected and recycled.
It only takes 5% of the energy to recycle a can that it would take to make a new can from raw metal. As a matter of fact, recycling is so prominent that the aluminum beverage can that you use today will be made into 6 new beverage cans before this year is out. So it's recycled constantly.
Anheuser-Busch runs one of the biggest and most successful recycling operations.
Consumers have several different options of how they want to recycle their aluminum beverage can. Some of them have curbside programs, others have voluntary drop-off facilities, others go to buyback centers.
At the buyback center, the cans are immediately weighed in bulk.
Once they hit the scale, that's what determines what is going to be paid to the consumer. The price varies based on what the individual buyback center is receiving for their metal.
Some recycling centers process tens of millions of cans a year. Nationwide, approximately 113,000 aluminum cans are recycled every minute of every day.
They are then put through what we call a baler. And what a baler does is it compacts approximately 700 to almost 1,000 pounds, depending on the baler, of cans into a bale. Those bales are then put into typically trucks, sometimes rail. A truck would carry about 40,000 pounds of bales, which would be about 40 large bales.
The bales are taken to a reclamation facility where they're melted down into molten metal, which is cast as new aluminum. This aluminum is then made into new cans.
This year, we recycled more than 27 billion aluminum cans.
Of course, cans weren't the first metal objects to be recycled. Ancient Romans would gather scrap bronze and melt it down to be recast as weapons. Resource shortages caused by the world wars greatly increased the need for recycling. People were encouraged to donate everything from old automobiles to tin cans in order to increase the metal supply. But it was during the 1970s that recycling beer and soda cans became commonplace.
As the environmental movement was taking off, the waste that was going into the ground in terms of landfills was just found unacceptable. And recycling as a way of controlling waste became very prominent in the American mind and around the world. It also turned out to be a really good idea because recovering metals, particularly aluminum more than anything else, actually pays for most recycling.
The aluminum can industry paid more than $1 billion in the last year to consumers, municipalities, and businesses to recycle those aluminum cans.
Another way can manufacturers are saving resources is by streamlining the cans themselves. They've become lighter. Since the 1970s, aluminum can weight has dropped from 55 pounds per thousand to 29.5 pounds per thousand. This is accomplished by what is called geometric optimization. A new super end is literally allowing can makers to cut corners.
A recent example of geometric optimization, or the kind of lightweighting that we can produce with technology, is through our super end beverage technology. A traditional beverage end has a nearly vertical wall at this position. You can see the difference with this super end, where the wall is about a 45-degree angle. Now, that fairly simple sounding change has had quite an impact. By using a 45-degree angle, we can save over 10% of the metal in the end. That's a very significant savings. By the end of this year, we will have produced 100 billion of these ends. That will have saved about 25,000 tons of aluminum.
Decades of can shaving has produced a metal-saving miracle.
This container was produced in 1971. Today, 4 containers can be produced with the same amount of material.
Light and lighter aluminum cans may hold our beer, but we need real heavyweights to hold some of the most toxic substances on Earth. Cans are the go-to container for an incredibly wide variety of substances. Today, over 1,500 different types of products are preserved in over 460 billion cans per year. But certainly one of their most demanding jobs involves storing radioactive nuclear waste generated as a byproduct from the processing of nuclear material for national defense. The material is highly radioactive and will be for thousands of years. The Defense Waste Processing Facility at the United States Department of Energy's Savannah River site in South Carolina carries out the important process of storing nuclear waste safely.
We have the full array of materials that are produced in the production of nuclear materials in reactors. We do have some amount of plutonium. We have technetium.
All of the waste processed here has been generated by Savannah River site reactors. The first step is encasing the radioactive nuclear waste in glass. The procedure is called vitrification. The nuclear waste enters the vitrification process as a form of sludge.
It comes from the dissolving spent reactor fuels that have been in nuclear reactors, where it's stored in underground tanks, roughly 1 million gallons in each tank.
This vitrification utilizes a material called frit.
This is frit. It looks like what it is. It's sand. It's a special kind of sand. It's a special recipe that we've had made that allows it to bond with the waste, and when it cools, form a glass that is inert and lasts for a long period of time.
At Savannah River, the sludge and the frit are glassified in a melter.
It looks like a big teapot, and it's a cylindrical object with a pour arm that comes out of it, and that has 4 electrodes that basically are shooting lightning bolts back and forth through this waste and heats it up to 1100 degrees centigrade, where at that point the mixture is molten.
The molten glass is poured into the canisters through a special bellows assembly. All of the work is done with robotics because of radioactivity. The canisters are specially designed and manufactured for the vitrification process. They weigh 1,200 pounds, and their sides are 3/8 of an inch thick.
The canister itself is about 10 feet high. It's about 2 feet in diameter. It's made out of stainless steel, and we'll be pouring at a rate of about 1/2 gallon per minute into this canister. It takes roughly 24 hours to fill a canister.
The canisters were rigorously tested before they were approved. Especially important were the drop tests. Because the canisters will be transported on public roads, they must be capable of withstanding any impact that might occur if there were an accident.
It was drop tested from a height of 7 meters. It was drop tested right side up and right side down, and it had to survive that drop test without any damage that it would affect its function, and it's done that successfully.
For decades, scientists have sought an effective way to store nuclear waste for long periods of time. They looked at many options, from burying it in the ocean, to placing it in polar ice, to sending it to outer space.
The concept of vitrification was selected as the best, and the main factors that got into that was the incredible stability of the glass form for thousands and thousands and thousands of years, the availability of melter technology for this application, and those were probably the dominant factors that caused it to be chosen.
Although strong, the canister itself doesn't prevent the radioactivity from escaping.
We use it as a vessel to capture the glass and let it set up, and we use it to support transporting the material from here to storage in a federal facility. So we had to have a can that was about the size that could move on public highways.
Once the molten glass is poured, it is allowed to cool. Then the outside of the canister is decontaminated.
That is like a sandblasting process. We'll put it in a cell and spray it with nozzles that spray water and sand. And we will knock all of the corrosion and the surface contamination off the canister.
Although the waste has now been vitrified, radiation still emanates from it. So it must still be handled robotically, and no one can approach the canister without being shielded. The radioactive materials will eventually become harmless, but only after thousands of years of decay. The canister is sealed by welding a plug into its top.
We use over 40 tons of pressure and 250,000 amps of electric current to place a welded plug in that canister in less than a second and a half. That's a lot of energy in a small place in a short time. That process produces a very reliable weld that's robust and has been tested and proven for thousands of canisters.
After being welded shut, the canister is transported to a storage area.
We have a special vehicle that transports the canister from our shielded building to the shielded storage areas. It's a large vehicle. The diameter of the wheels is about 4.5 feet. An operator positions hydraulically the shielded cylinder and the cranes to both lift the canister up into the vehicle, and then when the vehicle reaches its final destination, to remove the shielded plugs and place the canister in its assigned storage location.
The storage area at the Savannah River site is only temporary. The government's plan is to someday transfer the canisters to a permanent federal repository for high-level waste, probably at Yucca Mountain, Nevada.